The second question regarding transpose of mapping. Find T transpose of phi of x, y, z, where phi R2 to R defined by R2 to R is defined by phi of xy equals to 3x minus 2y, and T R3 to R2 defined by T of xyz equals to x plus y plus z, comma 2x minus y for x, y, z belongs to R3 type element. Now solution. We have phi R2 to R is defined by phi of xy equals to 3x minus 2y, and T R3 to R2 defined by T of xyz equals to x plus y plus z, comma 2x minus y for x, y, z belongs to R3. Therefore, T transpose of phi of x, y, z equals to phi not T of x, y, z. By definition, we know that T transpose of phi equals to phi not T. So this is equals to phi not T of x, y, z. That is equals to phi of T of x, y, z. That is equals to phi of, now what is T of x, y, z? T of x, y, z equals to x plus y plus z, comma 2x minus y. So phi of x plus y plus z, comma 2x minus y. That is equals to, now phi of xy equals to 2x minus y. So यहाँ पर x के जगह पर x प्लस वाई प्लस z है, और y के जगह पर 2x माइनस वाई है. सो 3x के प्लेस पर x प्लस वाई प्लस z माइनस 2 इंटू वाई के प्लेस पर 2x माइनस वाई. दैट इज इक्वल्स टू माइनस x प्लस 3y प्लस 3z for x, y, z belongs to R3 type element. Now third question. Let T is mapping from V to U be a linear mapping and V be finite dimensional. We have to show that car T transpose equals to imaginary part of T transpose whole knot. Solution. We have T V to U is a linear mapping and V is a finite dimensional. Therefore, T transpose is defined by U star to V star. Is a mapping from U star to V star, which is defined by T transpose of phi equals to phi naught T, which is just definition of transpose of a linear mapping. Here car T transpose contains in U star. Okay, let phi belongs to car T transpose. Therefore T transpose of phi equals to 0. That imply we know that T transpose of phi equals to phi naught T. So phi naught T equals to 0. Now let U belongs to imaginary part of T. Therefore U equals to T of V for V belongs to vector space. Now phi of U equals to phi of T of V, that is equals to phi naught T of V, that is equals to 0 of V, that is equals to 0. 0 of V, that is equals to 0, because we know that phi naught T equals to 0. Therefore phi of U equals to 0 for all U belongs to imaginary part of T. That imply phi belongs to imaginary part of T whole not. Therefore car T transpose contains in imaginary part of T whole not. Now let phi belongs to imaginary part of T whole not. Therefore phi of U equals to 0 for all U belongs to imaginary part of T. Let V belongs to vector space V. Now T transpose of phi of V equals to phi naught T of V, that is equals to phi of T of V equals to 0, since T of V belongs to imaginary part of T, for all small v belongs to vector space V. Therefore T transpose of phi equals to 0. That imply phi belongs to car T transpose. Therefore imaginary part of T whole not contains in car T transpose. So we have shown that imaginary part of T whole not contains in car T transpose, and car T transpose contains in imaginary part of T whole not. Hence car T transpose equals to imaginary part of T whole not.